Okay, so we have this information on X, and rather than gather more data to derive our mean and standard deviation from the data, we're going to use the data we already have, the transformation, to get the mean and standard deviation of Y. So the way I explain this is we use the mean operator like this. And basically what we're doing here is we're multiplying every value of the distribution of X by 100, and then we're adding 500 to each value. So how does that affect our distribution? Well, this one, if you imagine having, let's just make it symmetric. Doesn't necessarily have to be, but just to visualize. So if I was to multiply every value of this distribution by 100, how would that look? So we have, this is 6.7 here. So what would be the new mean if I multiplied every single value by 100? If I multiplied every value by 100, what would happen to 6.7? Okay, so that would become 670 in the middle. And then let's say there was a value here that was, okay, let's do one standard deviation. So one standard deviation would be 6.7 plus 2.4. And that puts me at 9.1. Okay, so what would happen to 9.1? If I times every single value by 100, 910. So where's that going to be on this drawing? Well, it depends. If I want to use this scale, then that's going to be way over here, right? If I'm going to, so this is going to be much more spread out, over here. So one standard deviation would be over here. So what's that going to do to the distribution? How would you describe what that does to the distribution? No comments? It's going to flatten it, right? Relatively speaking, it's going to flatten. So x times 100, 100 times x. So this is the x distribution. This is 100 times x, and it's flattening it out. It's more stretched out. What's another word for that? Describe it. Spreading, spreads it out, spreads it out. Let's say spread. More spread out, right? Okay. And what happens then if I add now 500 to every value? What would 670 become? 1170. Okay, so now the new for 500 plus 100x, which is y, it would be pretty much the same shape. I'm gonna just put that. I didn't make a great drawing, but I hope you get the point. So it's pretty much the same shape, but it's going to be centered at 1170. So it shifts it over along that number line by adding 500. But it looks the same otherwise, right? It's just the same spread. Do you agree? All right, so I'm going to move it a little bit up. Trying to make it look the same. Okay, so what does it mean? The mean change. How did the mean change? You guys, whatever you did to the value, whatever you do to x, you also do to the mean, you see? So the rule is that you're going to do the same thing to the mean that you did to x. So I also write it with like a mu symbol because this is the distribution. So I can write using the operator that mu of y is 500 plus 100 mu of x. So whatever I do to every value, I also do to the mean. It's an important rule, and it's in the box in the notes. Let's see, let me go back here. So that's like the first box, one of the first box here, okay? Page 37. Sorry. All right, so then the issue is, what do I do? What happens to the standard deviation? Or variance? Let's deal with the variance, because the results come from the variance. Okay, so everybody, okay, first of all, did you understand this first discussion here? Actually, maybe I should calculate it. So let's take the calculation. So then what is the calculation before I continue? Because sometimes I get carried away. So this is 500 plus 100, which we actually did ourselves already. The expected value was 6.7, and that's how we got it, right? So you guys, we already did it, but I just wanted to show you that you can use the formula, you can think through it, and that's the value there. All right, so now what about here? What happens here? Okay, let's do the reasoning. What happened to the spread? We already discussed it. Initially, it makes it flatter when we multiply by 100, but the 500 didn't do anything to the spread. Do you agree? The 500 doesn't do anything to the spread. So really, when it comes to variance, there's no effect of a constant, adding a constant term or shifting the distribution. So all that's going to matter is this. And in fact, the term in front here, has an effect, the variance will actually be 100 squared times the variance of x. Why is that? Does anybody know? Why not 100? Why not 100? If you think back to the formula for variance, go now, remember, I don't have data here, but data was used to calculate the variance of x. And if we use, let's just say we had a sample and we used the sample to attribute to the greater population. So remember the form for variance or standard deviation is the average of the square deviations from the mean. Remember this formula? So this is like our S. If I take out this, then this is the variance. Okay, so if I just had a sample, well, what if I don't, okay, first of all, you guys remember this, right? So this is just the average of the squared deviations from the mean. Well, let's say it's not X I have, but I have 100X. Well, what's 100X? Well, 100X would look similar, but in front of each X will be 100. So basically I take every value and I put 100 in front of it, or multiply every value by 100. Well, the average will be 100 times the average, which we learned up here already. So that's what's going to happen here, right? Whatever I do to every value, I also do to the mean. So this one will be 100, and this is just showing that I've multiplied everyone by 100. Okay, so what can I do with the 100? I can factor it out to turn this into something that looks, again, like this. I can take this, and factor out the 100. But is it coming out as 100 or 100 square? Okay, so I can pull the 100 out, but to bring it out, it gets squared. So that's why, because the whole thing about the variance, remember, and if I pray you watch those videos, I explain why we had to square was because of the issue that we're centering at the mean at the center of gravity of a distribution, and the deviations above the mean and the deviations below the mean will cancel each other out unless I change the sign. So this is what I'm doing. I'm squaring them. But then effectively that affects the scalar in front as well. So that's where the square is coming from. Okay, so this is the rule here. Okay, and I have that also in a box. And that translates into the standard deviation, which is the square root of the variance Okay, so if I'm going to put that in symbols here, that's 100 squared. Vx is sigma x squared. I take the square root and I get this. Okay, so sometimes I write Vx, sometimes I write the sigma squared. It's just because this action V of this is just showing the steps of using the operator, the function on the transformation. I can't pull myself away from that. So then I take the square root and I get this. Okay, so the rule is in the boxes back on page, I think over here. Page 40. The best thing is that you understand it intuitively. So see, this is what we just did. If you have a linear transformation, a plus bx, it looks like a line. That's why we call it linear transformation, but we're multiplying by something and shifting it. So this a disappears. And we explain why, because just shifting something doesn't change how spread out it is. So that becomes that. And then the square root of that is just this. That's what we just did, these two boxes. Okay, we're making our way through the boxes. Very good. And so you have the rule for variance, sorry, and the one for standard deviation both. The standard deviation one's like less messy. So those boxes, you guys can put them on a page, summary page or an outline for your studying, and that's what the boxes can be translated. Make sure that you transcribe them properly. Don't make an error, or you're gonna have trouble. Okay, so now we found the standard deviation. We can calculate it. And the standard deviation is going to be 100 times the standard deviation for x, or it's going to be 240. And that's it. So what we did was we generated a new variable, and without collecting data on that new variable, because we know about x, we can, by the virtue of the rules, we can calculate the expected value or the mean of the new variable and its standard deviation. Variance too, but I really want the standard deviation in the end. I like the standard deviation because it's in the units of the problem. So this is dollars. Let's put the dollars on it. These are dollars and these are dollars. Any questions? So you should be able to do a problem like that. That was page.
Professor,
Uh-huh.
um, how can I apply this on real life if I'm trying to monitor my sales? If I have a company and then I have sales, how can I apply this?
If you have a company and you have sales, well, it depends. What do you want to improve sales always, right?
Exactly.
So, so I've just shown you how much more of an expense you would have. Um, well, if you have information on a population and you think there's going to be some factor of population growth or a sector that's going to grow or change in some particular way, you can estimate future sales by making an equation of how you think it's going to shift things. Does that make sense?
Okay, so this helps me to identify if I need to increase my sales in a specific sector, or if I need to
Yeah, if
make
you need
more.
more product, let's say
Mhm.
you need more product for a particular sector that you know is growing, and you can make some adjustments to say, okay, I think that the population is going to amplify because of advertising, it's going to double or triple, right?
Okay.
Then you can do that equation sort of thing here. And but if you know that there's also yeah, so if you're basing your sales on population, and then maybe some other shift factor because of advertising, um, let's say you're going to buy ads on some app, and you expect that you're going to have like a fixed amount of people are going to see this, and you can have a shift factor too. So yeah, something like that. I think you understand, right?
Thank
Yeah. So yeah, we did this is a cost example. That's an example of estimating sales changes because of advertising. And you can make an ambitious estimate, or you can make a, less ambitious estimate. And then you have an idea roughly of what you need to provide in terms of products, or purchase in terms of the supply chain. Make sure you have enough product. Okay, good questions. Let's see. So this one, so I have some finance examples that I use, and this one is similar, you see? So don't get intimidated by the different letters, right? This is just mean, this is standard deviation, and I mentioned correlation, so we'll talk about that. So here's my new variable, but how is this different from what I just did? What's different here? I'm cutting through the information, so what did I do here? What's different between this problem and the one that we just did? Two variables, and the constants on both, right? So this is different. This is not exactly a linear transformation of one variable to create another. These are two variables to create a third variable. So R is the new variable. You probably want to see X, Y, and Z, but anyway, don't get thrown off. This is a new variable created by two. So we have rules about that too. So it's going to be the same thing, whatever I do to the value. So I'm going to combine these in a portfolio. And you have to be aware that if I'm combining X and Y in a portfolio, I'm going to do, something to X and something to Y to create an R. So the rule about the means is going to be the same. Whatever I do to the values, I also do to the means, right? So that's going to translate here. And then in terms of the variance, the catch here is that I'm going to still use the rule that I taught you here. Here, this sort of thing here where, right? But there's one catch. Do you know what it is? So I can do this for X and this for Y, but I also have to consider the correlation of X and Y, because if I have two things together, I have exposure, and there's risks by holding them together. So in addition, that formula changes. And you see here, this looks confusing. Hey, hold on. Let me go back to the boxes. Okay, so here, if I put X and Y together, and there's no scalar in front, there's no multiple in front, but it's okay. The rule is you square the first one, so you get the variance of the first one, the variance of the second one, but you have an extra term. This extra term is because you have to consider the correlation between X and Y that will contribute volatility. Now, sometimes having X and Y together reduces the volatility because X and Y might be negatively correlated. So this could be a negative and it can reduce the variance. But if it's positive, it adds to the variance. Okay. So that's what this term is here. And this one is interesting. Okay, so let's just let me explain this first, and then we can go for the rest, all right? So, okay, so let me just ask you at this point, did you guys watch the video of me explaining this formula? How many of you saw that video? Or maybe you don't know what I'm referring to. Once I start, you'll understand. So when you have two variables, and I'm going to do this for the exercise that I'm talking about right now. And rather than point 2 and point 8, I'm going to talk about A and B. So what I want to do is I want to consider in pairs using a matrix the covariance, the contribution in going in pairs. So the covariance of the scalar x with scalar ax, and then this one, so whenever I do a matrix, I always take this one first, okay? Now I'm going to do the matrix by ax and covariance by. Okay, so how many of you saw me doing this in the videos? Nobody? Okay, so you're going to appreciate it. So tell me what is this? I've written it like this because I'm going to take them in turn. But what is this? So take a moment, express it, write it out. What would this be? Just like I did over here. Like, how would that work? How would that look? So this will be covariance ax. Sorry. Is equal to, so what's covariance? Let's remember n minus 1. I have to write ax minus ax bar squared. Oh, sorry. So covariance is, so remember the formula for covariance. If not, check if you have a sheet of formulas or go back to your notes. This is covariance of this. Do you agree? So it's weird because I've never shown you covariance of something with itself, but the covariance of something with itself is essentially, what do we call this? I can factor out the A and this A, and what do I get? What will be in front? You guys see it? You guys see, you see anything familiar here? What do I get if I take out the A's? Okay, we're going to do this and then take a break. You guys need a break. You need to refresh, reboot. Somebody tell me. A square, Jose Juan. A square, I get A square, and then I get this. What is that? What is that? Anybody recognize this? This is the average of the deviations from the mean, which is called the variance. So the covariance of something with itself is the variance. If you put a scalar in front, you get, well, in this case, they're the same scalar, so it's a squared, but it could have been ab, and then it would just be ab in front. Okay, so this is the beauty of this elegance of math is, going back and understand, not just memorizing rules, knowing where things come from. So then this is going to be a squared variance of x. Got it? So from now on, whenever we see this, we know how to simplify it. This one is going to become a squared variance of x. And now you're going to tell me what this one becomes. So sigma x squared. So what will this one become on this diagonal? B squared sigma y. So what I've shown you is I explain now where these come from. We got this one. Well, actually, this box here. If we have covariance of ax by, we get ab covariance xy. I'll just add below that if you have the covariance of ax, like this is the more general case, right? That the one that's in the box is the more general, but if it's the same thing with itself, this is a squared covariance xx, but the covariance xx is just the variance. Okay, so that's what we showed. Now we're going to use this one, this is the absolute most general, and get the other terms on the matrix. And what we're creating is this formula here. We got this one, we got this one. This one didn't have a scalar in front, so it's even more easy. And then we're going to get this one. That's what I'm going to explain next. All right, so let's do this here. Covariance of ax by is equal to, I mean, basically I showed you the answer. So what is it? What is it? So if we did step by step, I would just replace this one with a by. And so I'm going to take out the a from here. And I'm going to take out the b from here. So it's going to be ab, and it's going to leave the formula for covariance. So this is ab covariance of xy. So this is going to be ab covariance of xy. And now, what will this one become? Is this one different from that, or is it the same thing? Can you imagine if I just reverse these, if I put these brackets on in the other order, I put this one first and then this one after, will it change the result? Yeah, Yeah, Yadib says right. It will not change the result. So this is the same thing, guys. This is the same thing. So that's where the 2 comes from. Okay, so I've shown you how this matrix gives us the formula that you can see the pattern. So if you can see patterns, you're not going to have any trouble with this, right? This is just a pattern. So putting all these components of volatility together, we get the formula in the box. Let's try to write it out. So the variance of AX plus BY is equal to A squared variance of X. Don't forget this square is necessary for variance. B squared variance of Y plus 2 AB covariance XY, which I cannot go any smaller. Okay, so questions. Let's take a break and then we're going to do the last few formulas there and get on to binomial in the next hour. We got to look at binomial. Okay, let's take 5 minutes. You can ask me questions when we get back. Okay, so let's pick this up. So all I've done here is for 2 variables, deriving this formula. Now, what if it's a different formula? So it's not AX plus BY. What if we look at this formula here? What if it's X minus Y or AX minus BY? Can somebody explain if this is correct? It's not correct? Is it correct? So we have var AX plus BY, to be more general, would be A squared sigma X squared plus B squared times sigma Y squared plus patterns. Stay with me here. So this is going to be 2AB covariance XY. That's what we just derived. Agree? What if you have variance AX minus BY? What would be the answer? It's going to be A squared sigma X squared plus, so now I have to square this term. What you're going to do is take the negative with the B, okay? Because we're going to use this. So what we're going to do, in other words, is VAX, because we want to use the original rule, plus minus BY, like that. And what does that become? Let me erase this here. Me and my white. So these are the same. So this is going to be, let's do this, a squared sigma x squared plus, you see, negative b squared is just b squared sigma y squared. So that's how that works. But then when I have to add 2ab covariance xy, I have to put the negative in front. Let me do that again. This is going to be a negative here because it's negative AB, right? When I multiply those. So that's how you get that formula. So basically, I'm using the original formula with the derivation that we just did together, and I'm combining the negative with the b here, and so I square it, and that removes the negative because a negative times a negative is a positive. And then this is going to be because you have a times negative b, and you have to put the 2. That's where that comes from. Got it? Okay, now, so that's basically it. I mean, I can, this is, this one is the most important, right? Because I use this one to get this one. So this is the most important, and it's just, it's this one with the A and the B in front. So you need to realize the more important thing than these formulas, these are like a conclusion. The more important thing is the root, the method, the matrix method. Taking the matrix, I can do this not just with two variables. See, this was the example that I gave was about combining two stock or two investments in one portfolio. But usually when you make a portfolio, you have more than just two things in it. But we can use the same principle using the matrix and make even a longer formula. So we're going to look at that next. First, I want to tell you that this box here is just telling you to use the matrix method that I just taught you. That's all it's saying. It's saying take the two variables or three variables or four variables, however many you have. You see, they say n. However many variables you want to add together, you see? And so it's adding so many variables together to get the variance. You have to use the matrix method, taking two at a time, and derive your own formula. Okay, that's what it means. So let's repeat this for three variables, just so you can see how it works, and then we're going to answer the next set of problems. This one's here. Okay, so let's do the matrix. So I'm going to make this a little smaller. Let's do the matrix for three variables. Let's see. I'm going to write them down and you're going to work on it, okay? AX, BY, CZ. And then AX, BY, and CZ. So find me the formula for three variables. So I'm going to get the variance of AX plus BY plus CZ. So I basically created a new variable, call it R, three assets or three investments in one. I'll pause the video, give you a little time, and you're going to tell me what is the result. And if you can just guess, I mean, using the pattern, if you have an idea of what the pattern gives you, that's fine with me. Okay, so I'm just cleaning this up. All right, so now we're going to write it all out. So the first one is always in the row, AX, BY, and then covariance AX, CZ. And keep going, covariance BY, AX, covariance BY, BY. I can do the diagonals first. Covariance CZ, CZ, and then covariance BYCZ, covariance CZ AX, covariance CZ BY. Now, if you don't want to do that and just want to jump to the results, I'm fine with that too. So let's do the diagonal. This is going to be A squared sigma X squared. This is B squared sigma Y squared. And this is C squared sigma Z square. So those are done. And now I'm going to take these in pairs. These are going to be the same. These, oops, let's use different color. These are going to be the same. And these are the same. And that's where the 2 comes from. So it doesn't become a 3 covariance. There's still 2. They're still in pairs. Okay? So you can see the formula here. This is going to be 2AB covariance XY. The greens are going to contribute to, you're not going to see that very well. I'll just do it in red. This is going to be 2AC covariance XZ. You see the pair? And then yellow here, it's going to be 2 BC covariance YZ. And that's going to be the formula. The formula is going to have 3 diagonal terms and then 3 with the pairs. The main thing is that it's going to be 2. Just because I add more variables doesn't make it become 3 or 4 or 5. It's still conducted on a matrix in pairs. So you get the 2. And so now you can answer questions that other problem set. Let me show you here. Okay. So this one we know, we just did it. We did those 2. And then this one. So I'm going to write out this is going to be A squared sigma X squared plus B squared sigma Y squared plus C squared sigma Z squared. Remember, when I add them, this negative gets squared, just like I did here. And then it's going to be plus 2. So we do it in pairs. AB covariance XY plus 2 AC, but C is a negative, so it needs to go here. I don't lose the negative now because it doesn't get squared off. Covariance X and Z. And then the last pair is BC minus 2 BC covariance YZ. You guys see it? So if you guys, you don't have to be mathematically inclined. You have to know patterns though, which is pretty much math. So I had a mathematician professor who used to always say math should be in the arts faculty because of these patterns, it's very elegant. All right. Any questions about this? Did you need me to write out the formula all as one line over here, or you're okay? You know what to do. You see all the components. All right, so you guys, we did this together. I mean, you struggle maybe, but now you understand a little bit better. I did all of this now. This one is now applying it to traveling, and it makes you think about the vacation you're going to take in June or July, right? I like this example for the end of semester. So in here, you have information. I'm kind of jumping. The answer is given, so you guys have that as a resource. But here you create a new variable combining the weight of your carry-on and your check bag to estimate the total weight you're going to contribute. And then we actually estimate the weight in the plane. I have a lot to say about this because recently I was given a status on the plane and I had no idea what I was missing. Wow. I really like having that status because you get upgrades. And so, yeah, and I got that. I think they had a initiative to bring people, to incentivize them to fly more. And they offer them these perks if they fly enough. And I just realized that there's people who put more than 50 pounds in their carry-on, I mean, their check bags. I had no idea. I thought you had to pay for that, but if you have status, you don't. You can bring 70 pounds. So anyway, without going on to all of that, this is a very practical exercise. And I go all the way to check that we do not exceed the allocation or the allowed weight on the plane for total customers on average, right? On average. All right, so any questions? Anything you want me to talk about again or go back? Because I want to do binomial stuff for half an hour. I think this needed a little bit of attention, but not too much.
Professor, I have a question.
Yeah.
On the variance of just what we did. So if the
This
variables
one?
are independent, yeah, but I meant page 41
Okay, yeah, I didn't talk
in
about that.
the
So if they're
yeah,
independent,
so
then covariance will be 0 and that term disappears.
okay, so you just add the variances from the two variables. Is the independence always
If you remember this rule, and
yeah,
if they're independent, this one disappears because this is 0.
okay. Oh, wow. So the independence is always gonna be given in the exercise.
Yeah, yeah, it will be
Okay.
clear because you can't assume it.
Oh,
So yeah, thank you for reminding me. So that the special case is when they're if two variables are independent or not correlated, that will be 0. Okay, so that term disappears and you just get these two. All right, so we're going to go to talk about binomial for a bit. All right, I do spend some time discussing how to identify if you have a binomial, how to distinguish between a binomial and non-binomial events. And then I also spend time making calculations. So let's talk about the origin of the formula. This is, for me, this is pretty straightforward. I demonstrate the origin of this formula, the logic behind it. I introduce this expression, something different, but if you have your calculator, you guys can do this in your calculator also. I did show you how to do this in Excel, right?
Excuse me, Professor.
Yes.
If you're presenting, we cannot see.
Ah, okay. No, I forgot. Let's go. Okay, so I did show you how to do this in Excel. And I'm fine if you use Excel, but if you do use Excel, you need to upload that Excel file if you're not going to write out your work on separate pages and scan them. Okay, so I want to see your programming if you use Excel. So this captures the probability of seeing a particular outcome from a binomial scenario or setting. In a binomial setting, there are two possible outcomes, which we refer to as what you're looking for, the success, or not getting what you're looking for, the failure. We also need to know the probability of seeing that success, and then indirectly, we know the probability of a failure, right? Because it's 1 minus the probability of success, P. And we need to look for our success a repeated number of times that is also known, but fixed. You can't keep looking and looking. That's not a binomial setting. You have to look for a set n number of times. It's known, finite, and fixed. And each time you look, the setting is identical. The chance of seeing a success remains the same. That's known as independent trials. So if you have that set up, then you can calculate the probability of, well, any one of these possible outcomes. So if there's n trials, let's say there are 10 trials, how many possible outcomes are there? Very good, Natalia. She knows where I'm headed. Okay, so remembering always that it's possible that you don't get to see any successes. So you have to have that extra 0. So that's why it's 11. So the answer is 11. Okay. And this is the formula here that captures the idea that really it uses the rule for independent events and their joint probability or their probability of happening together. So I explain here the origin of the formula using an example. The one that we're familiar with is that of throwing flipping 4 coins and observing how many tails appear. So you could either get 0 tails, 1 tail, 2, 3, or 4, depending, because we flip 4 coins. So there's 5 possible outcomes. I've listed them here and how they might look. Now we know the probability of each individual event. We know that because they're equally likely, each one is 1/16 because there's 16 possible arrangements and each one is equally likely. But now combining them by definition, as the number of tails observed in 4 flips, we group them like this, and now we can count what's the probability of each one. 0, 1, 2, 3, or 4 tails. Now, this is how we dealt with this problem before. Now that we have the binomial formula and we've identified and labeled this as a binomial variable, we can just use the formula, but I want to derive the formula. And the way that I do that is I start here and I say, go for tail, tail, head, head. So basically, what's the probability of this event? Well, we know it's 1/4. I mean, 1/16. But let's do this another way. Let's just use the logic rather than doing, there's 16 possible outcomes because we list them all, and we're able to we're just able to count, right? How many there are. Rather than do that, because what if I said there's 10,000 possible outcomes and you're going to sit there and do all the possible arrangements? No, you're not going to do that. Instead, we want to try a more take advantage of the patterns, right? A systematic approach. So tail and head exactly in this arrangement, in this order, would be the same as, because of the rule of independent events, I can just multiply the probabilities, and that's how I get that result. So I get like that, but I want more of a pattern. I don't just want the result. I already know the answer. I knew the answer way back here, but I want to get a pattern going. So I'm going to call, in the definition of successes, I'm going to call this a success, and it's going to have probability P. But this is also a P, and now this, because it's the only other outcome, this is known as 1 minus P as the probability, and also that's 1 minus P, right? Because there's only 2 possibilities. So I'm using the complement rule. I'm using all my rules here, it looks like. So then this is going to be written as P squared and 1 minus P squared. Again, I could punch in all the values, but that's not exactly what I'm interested in. I'm interested in this pattern. So I can use this approach for 2 tails, but then I noticed that there's kind of a something to exploit here, this pattern. So 2 actually represents that I want for 2 successes or 2 tails. So that's what that is. That's actually the number of successes. And if that's the number of successes, this one is the number of failures. The number of failures is n tries minus k. I use k as the symbol, and I refer to it as my special K, the cereal, the branding of the cereal. So this is my special thing that I'm looking for. It's the one out of all the possible outcomes. What are the possible outcomes again? X could be 0, 1, 2, 3, or 4, but I don't want to get all of them. I just wanted to get this 2. So that's going to be like my special K for that question. That's what I want. So K represents the number of successes I'm interested in. And because that's the number of successes, n minus that, total number of trials minus the number of successes, is the number of failures. So that's where the formula is coming from in general, to solve for the whole thing. Like I just got one of them. Sorry, I just got one of them, and I want to do, just this one. So that'll give me the result for just this. But what if I want the whole thing? Well, the whole thing includes all these arrangements. And there's 6 of them, but it's not always going to be 6. Like this one is 4. So I need an approach to know how many ways are there to see 2 successes in 4 trials. Well, we have that. This is something you should have learned in high school, but if you didn't, you're going to learn it now, and we're going to use our calculators to compute it. And it's actually, the principle is in, it's the area, it's like combinatorics, it's referred to as, but it's probability theory, I guess, but it's specifically combinatorics and arrangements, right? How many different combinations are there to see 2 successes in 4 trials. That's what that's giving you here. So 4, this is called 4 choose 2 or n choose k. And you can get this in your calculator. Now the calculator that I gave you for second function NCR 2 will give you 6. And I spent some time emphasizing you use that. So that's the number of ways that you can see 2 successes in 4 trials. Now this stuff here, the factorials translate into, this means 4 times 3 times 2, and then this similarly 4 minus 2 is 2 factorial. So this expression actually translates into factorials. That gets you 6 manually, but if you don't know that, it's fine because you're going to use your calculator, okay? So that's where the formula comes from. So the formula for x equals k is n choose k, p to the k. So k is, so the number of successes, so the probability of success to the power of the number of successes, and the probability of failure to the number of failures. And we're basically doing this. But then we have to consider all the possible ways of seeing that 2 successes. That's what we need this for. This one we get out of our calculator, and you can multiply straight across. I'm not sure exactly what you guys are using, but if you're using the calculator I gave you and you have it in mode AOS, it should be no problem just to multiply straight across, because that honors order of operations. All right, so we have some time. I also spent some time talking about the symmetry, which becomes important for the relationship between this. Okay, so we are talking right now about a binomial distribution. A binomial distribution is not a continuous distribution, right? It's a discrete distribution. Remember, I can list all the possible outcomes. It's not infinite like in a normal distribution. And I discuss in SDS how you can use the normal distribution as an approximation to the binomial, which is very mind-blowing, right? You're going to go from a discrete one to a continuous one, and how in the world are we going to do that? But one part of it is to see the symmetry here and exploit that symmetry. But anyway, I'll get into that in SDS. So I'm just recapping, and I did some calculations here. So let's do a couple of these before we're done. Which one do you want to do? If you've done them all, or... So all of these are binomial, but you also need to be able to identify whether a scenario is binomial or not. So when we solve this, let's try and do that, right? Do you have a specific one you want me to do? 5? 5. Okay. Yeah, that's a good one. That's a confusing one. Once I do it, it won't be so hard. But okay, so we're going to read this, and we're going to first read it to identify whether it's a binomial or not. Okay, so I do mention some other distributions that it could be, but we're really not going to make calculations for those distributions. We want to focus on the binomial distributions. So there are 4 patients with SARS in a Toronto hospital who are monitored by 2 staff members. Okay, so we have a few numbers floating around. We got the 4 patients and we have the 2 staff members. Let's keep reading and we'll see which one's relevant. Suppose the probability at any one time of a patient requiring emergency attention by a staff member is 0.3. So this is my only probability. So this is probably going to be my P. So let's say this is my P. So what we're gonna do is we're gonna identify X, N, P, and K. And let's see if we can express what is a success. What is it that we're looking for? What is it that we're looking for? Patients requiring emergency attention by a staff member. Patient requiring, so if a patient requires emergency attention by a staff member, that's a success. And that's not a nice thing, but that's what we're looking for, okay? Success doesn't have to be something we want to happen. It's just something we're looking for. So that's the, a patient requires attention. Now, this might be a little confusing because there's some assumption that's made here. And I'll get to that. So the success is a patient requires attention, and P is the probability of success. So let's fill that in. That's 0.3. So the chance that they require attention is 30%. This assume patients behave independently. Okay, so what is the problem? So it's giving me information on the patients behaving independently. Patients. So my patients are going to be my N, right? That's going to be 4 is my N. That's how I know, because it tells me that they behave and their needs are independent. If they weren't independent, I wouldn't be able to say this is binomial. There's 4 patients. The probability they need attention is 30%. Then this means that X can be 0, 1, 2, 3, or all 4. Okay, so we got everything. Now we're just going to go for the K. What is it that we're interested in? So we're interested, are we just going to solve for one of these or some combination of these possible outcomes? So the last sentence tells us what we want. It tells us about the K. What is the probability at any one time that there will not be sufficient staff to attend to emergencies? Which of these will be that case? So there were 2 staff members, and without saying it, there's an underlying assumption. Okay, so that each patient needs only 1 staff member. That's kind of like inside of this question, because you're like, oh, if it's an emergency, do they need all the staff? Or we'll just say, as long as they have 1 staff member, that's all they need, okay? All right, so K, when will there not be sufficient staff? Translate that into this. So there will not be sufficient staff if there's only 2 and there's 4 patients. There will not be sufficient staff if 3 or 4 people need attention. Okay, so what we have to do is get the probability for x equals 3 and add it to the probability of x equals 4. So let's write this up together. So I'm going to do probability x equals 3 plus, I'll do it in 2 lines, x equals 4. So what we have to do is how many ways are there to see 3 successes out of 4? Then I have to multiply by the probability of success to the power of successes. So it's going to be 3 successes. And then you're going to put here 1 minus 0.3 because this is the failure, though that's 0.7. And you're going to put here n minus k, which is going to be 4 minus 3, which is 1. So basically, these have to add to 4, the exponents, and these have to add to 1. You can check that you did everything correctly and just leave that. Let's do the next one. So how many ways are there to see 4 successes out of 4 trials? And then this is the probability of a success, and there's 4 of them. So the failure is going to be 0.7 and none of those. Okay, so if you can simplify or just plug this in to your calculator. I guess I'll show you the calculator. So you're going to say 4 second function NCR 3. So it's always going to be the case that the number of ways of seeing like n minus 1 successes out of n trials is always going to be the number of trials. Anyway, I think I believe I explained that. But anyway, it doesn't matter. You have your calculator in case you forget or you don't know that. So that's always going to be 4 times. Then I'm going to say 0.3 to the power of 3 and times 0.7. And I get 0.0756 for the first part. Do you guys get that? And then for the second part, this is a little easier. I'm going to just do it manually because 4 choose 4 or n choose n is always 1. How many ways are there of seeing 4 successes in 4 trials? You have to think like 4 trials, and how many ways are there seeing 4 successes? Well, there's only one way, right? So one arrangement. So it's always going to be like that. N choose n will always be 4 or n. And then this one is just going to be 1 as well, because anything to the power of 0 is 1. So all I have to do is 0.3 to the power 4, 0.3 to the power 4, so 0.0081. And I have to then sorry, I think we have like a tremor. My husband was freaking out. Do you feel that? Sorry, did you feel the tremor? No? Okay, we're very concentrated. All right, so let's add these together. Oh, maybe I do feel something. I'm on the 13th floor. Um, is that correct? Did you guys get that? Answer B? Very good. All right, questions for me. So that was like probably the hardest of all of them. And I think mostly because like, how did you know this? That's what confused me when I saw that question. And originally anyway, but you guys can ask me during the quiz, or you can state any assumptions you make if you're stuck, and I will consider them. So there's going to be 3 problems. I have to check. Let me see. Wait. Gotta double check. What did I do here? You can see it already. Number 6. Yeah, I said I would have 3 problems, and 2 are in the binomial, and 1 is with the rules of means and variances. And if you have to write something, you have the text box only for computational problems. That there's one computational and the other ones are just to read it and answer. Okay. Well, you gotta write in the text box, which you can do. But for the computational one, you guys can add you have to scan the page. If you have trouble scanning or sending it because it's confusing, just let me know. Alejandra, I'm working on the grades, sorry. It's never as easy as I plan. So, yeah, ASAP is my answer to your question. As soon as I can. This week would be great. There's been so much disruption with the Huelga too. I've had to make so many concessions. Let me turn this off. Recording. Well, I guess I can keep recording. So I've had to do so many things I never expected. What did I say? Maybe I didn't say anything. I'm gonna make you write them, answer all of them this time. You can do it. Don't worry, Omar. If it's really bad, I'll give you guys a break, but did you like my grading so far, even on the 2? Because I tried to give you a clave. Rather than discuss the answers in class, I gave you the claves for the answers, hopefully, and some feedback. And that's why it's taking me a while. All right, so you guys want to take a little break? It's going to open at 11, and I'll be here. Okay, so let's get out and pop back in for the test, and you guys can communicate with me if you have any trouble.
Professor, this is Omaira. Can I ask you something?
Yes.
Can you identify the name or the title of the test on the application?
Isn't
the
it
Moodle application?
you don't see test 6. Do you see it?
Test 6? Okay, perfect.
You see
I'll
it,
look for that
Omaira?
one. Huh?
You see it?
Yeah, I saw that that Omar wrote it for me. Thank you.
Okay,